Good morning. This is the seventh session of thermodynamic relationship. Okay, we'll derive a few more questions on the basis of this relation. The next problem is prove that T del P by del T P minus P is equal to del U by del V at constant temperature. This is the question. We have to solve this one. Okay, so this is a very important question, and this question has been asked in several examinations. So you need to be careful. You need to understand with proper logic how to derive this equation. Okay, so let me start this one. Since in this problem U is involved, there should be some logic behind this one. If you start any question, first of all read carefully the question, and you have to find some logic. You need to find some particular logic so that the question could be started. So in this problem, U is hitting zone. This U is hitting zone because this U is involved. That means we have to use this first TDS equation in which internal energy is involved. So just this is small u, right? Okay. This is small u. Okay. So first of all, we have to write as per TDS equation. We know that TDS is equal to du plus PdV. We are very familiar with this equation. So from this equation, this du will be TdS minus PdV. And this TdS, once again, as per equation number 1, this TdS can be written as we know this as per derived form of this TdS equation. This TdS is equal to Cv dt plus T del P by del T at constant volume into dV. Now this is PdV. Okay, so we have to arrange this equation in this form. This is equal to Cv dt plus this dV is common. Okay, so write in this format T del P by del T V minus P dV. So this implies this du can be written in this form. This is equation number 2. So what we have to write, first of all write this TDS equation, and since U is involved, that's why du is equal to TDS minus PdV. Write this TDS equation in the right form. This equation can be written like that. Okay, so first of all, just we need to shepherd the equation in this form. Okay, so that's why this du will be equal to Cv dt plus T minus del P by del T at constant volume minus P into dV. Okay, so from this equation, if you observe carefully, Since same logic we have used this logic in previous question also. So u is function of, this implies from this equation it can be concluded that u is function of t and v. This is very important observation. This is very important observation where u is dependent variable, temperature and volume are independent variable. Okay, so this is very important equation, we have to reach over this one. Now we will differentiate. Equation number 3 partially. We get, if we differentiate partially, that means this will du is equal to du by del t at constant volume into dt plus du by del v at constant temperature into dv. Okay, let us suppose this is equation number 4. So now we compare equation number 3 and equation number 4. We have to compare this one. If you are comparing both equations, we will find that this coefficient, we have to look over this one. This both are same equation, because here in equation number 2 this du is written in this form, in this equation number 4 once again this du written in this form. If you comparing equation 2 and 4, we will get that this coefficient of this tt will be same, this coefficient of dt, this is cv is equal to du by dt at constant volume, and this coefficient of dv, this one should also be same. That means if you comparing the coefficient of dv in equation 2 and 4, we get that just comparing the coefficient of the dv in equation 2 and 4, we get what we get. This is equal to du by dv at constant temperature is equal to T del P by del T V minus P. This is the equation we have to derive. This is the equation we have to derive, and this is proved. Okay, so so this is very simple. Simply in this equation, in this derivation, we have to be careful. We have just u is the striking point. We have to think about this u. So as per thinking, if you concentrate on u, that means we have to use the first TDS equation. So write this TDS equation in which u is involved, and just we have to arrange. After arranging this and proceeding, just will reach out this result. Okay. Some important observation. In this question. Just now, this equation we know this equation. Okay. In this equation, just we are saying that this del P by del T minus this equation is. So I'm writing once again du by del P at constant temperature is equal to T del P dV minus P. Okay. So if you look about this one, del P by del T, so from RHS it can be written that what is the value, just I have to check this value of this term. We have to check the value of this term. What is the value of this term? from RHS, this is equal to T into del P by del T, V minus P. Okay. We know PV is equal to RT. Okay. So this implies del P by del T at constant V is equal to R by V, and this R by V is equal to P by T. So we have to put the value of this one in this equation. Okay. Therefore, this RHS is equal to, this is T into P by T minus P. This T will cancel out. This will equal to P minus P. This is 0. This implies del U by del V at constant temperature will be equal to 0. This is very important and interesting result. We reached on very interesting result. Okay, del U by del V at constant temperature is equal to 0. What is the meaning of this one? This implies change in internal energy with respect to volume at constant temperature will be 0. This is our important observation. Okay, this is very important. So change in internal energy with respect to volume at constant temperature will be equal to 0. Okay. So this is all about the observation. This is some observation. If you look carefully about this equation, you will get this one. We'll reach on this conclusion. Okay. Right. So this is very important. Okay, this is a very important equation. Next, now one more problem in this slide. I will solve one more problem. Next problem. Prove that del H by del P at constant temperature is equal to V minus T del V by del T at constant pressure. We have to prove this equation. Okay, this equation is, both equations are similar. If you look carefully this the Weber problem, we will see that there is some similarity in this question. Instead of U, here enthalpy used. Okay, so instead of U, enthalpy used, and instead of V, this pressure is used. Okay, so there is some important, it might be case that how this problem could be proceed. So if you look carefully, if you have understood the basic logic behind this the previous problem, then you may proceed this one without any problem. So what is the main logic this one? We have to think about this one. This enthalpy is involved in this problem. So whenever enthalpy is used, just we have to use this TDS equation we have. This is TDS is equal to dH minus VdP. So this implies dH is equal to TdS plus VdP. this TDS equation. Once again, this TDS equation in derived form, we have Cp dt minus T del V by del T at constant pressure into dP plus VdP. Okay, if you arrange this problem, if you arrange this equation, you will get Cp dt plus V minus T del V by del T P dP. Okay, this implies this du can be written in this form. Let us suppose this equation number 1, this equation number 2. If you look careful, this equation number 2, we can conclude that u is function of Tp. This is very important observation. Okay, now differentiate partially, we get what we get, du is equal to del u by del T at constant pressure to dt plus del u by del P at constant temperature into dP. Let us look at this equation number 4. Now we have to compare equation number 3, equation number 2 and 4. If you compare equation number 2, 4, and we have to equate the coefficient of dP. We have to equate the coefficient of dP in equation 2 and 4. If you comparing, then we will get that there's some problem is there. Instead of u, you should have write this is not u. This is not u. There's some mistake, okay. So there is some error happened here. So we have to use h. This is dh. Okay. This is dh. Okay. Sorry. So if you proceed, that means we have to compare the equation of, we have to compare the coefficient of dP in equation 2 and 4. If you comparing, then comparing coefficient of dP in equation 2 and 4, we get del H by del P at constant temperature is equal to V minus T del V by del T at constant pressure. This equation we have to prove this is proved. Okay. Now if you look carefully in this equation, some important observation also there. Some important observations. What is the important observation? If you can, it can written that this V minus T del V dt P can be written V minus T into V by T, V by V by T. Since once again PV is equal to RT, RT. This implies dV by dt at constant pressure is equal to R by P, and this R by P is equal to V by T. Okay, so therefore this V minus T del U by del T at constant pressure is equal to V minus V. This will be 0. So del H by del P at constant temperature will be 0. 0. This is once again, this is very important, interesting result. So after, if you look careful this derivation, we can say that it can be conclude that change of enthalpy with respect to pressure at constant temperature will be 0. Okay, this is a very important observation. So we need to be alert, we need to be careful, because this derivation can be asked in a directly question in different form. The question might be asked like that: to prove that the change of enthalpy with respect to pressure at constant temperature will be 0. That means we have to proceed. We have to proceed from beginning. Okay, so while solving such as a problem, just we need to be careful regarding several formulas what we have studied in this lesson. So this is all about some important problems of thermodynamic relationship. Thank you.